In this video, we're going to solve applied problems involving parabolas. Parabolas have a very interesting reflective property that we will use in some applications. A parabola that is rotated about its axis of symmetry generates a three-dimensional surface called a paraboloid of revolution. Any ray of light or sound traveling parallel to the axis of symmetry will reflect off the surface of the parabola and pass through the focus. Two main ways this property is used. In the image on the left, we have a spotlight or a flashlight. The light bulb is placed at the focus of the parabolic mirror. Now, incandescent light, which is not focused laser light, will travel in all directions. However, as the light rays emanate from the bulb, they're reflected off of the parabolic surface and focused to travel in a direction that is parallel to the axis of symmetry. In the image on the right, we have a solar oven. It is a metallic parabolic reflector with a pot filled with water placed at the focus. The principle being used here is that as light waves hit the reflective surface of the parabolic mirror, the light is directed to the focus, and the thermal energy will heat the water in the pot. And now that we've discussed a couple of the really interesting applications of the reflective properties of a paraboloid of revolution, let's solve an applied problem. In this example, we will be constructing a headlight. And the problem states, a sealed beam headlight is in the shape of a paraboloid of revolution. Its depth is 2 inches and its diameter is 6 inches. How far from the vertex should the light bulb be placed so that it lies at the focus? Now let's begin by sketching a picture of the parabola used to form the paraboloid. Now beginning with an xy rectangular plane from -4 to 4 on the x-axis and -1 to 4 on the y-axis. For ease, let's place the vertex at the origin with the intention of having the parabola open up. Since the headlight has a diameter of 6 inches, then the endpoints of the parabola will lie 3 units to the left and right of the vertex at the origin. Also, the depth of the headlight is 2 inches, thus the 2 endpoints of the parabola will lie at the points 3, 2 and -3, 2. Now, let's sketch the parabola from the vertex to these 2 points that we just plotted. Now, let's note that the parabola ends at these 2 points and does not continue through them. In other words, the domain of the parabola is from -3 to 3 on the x-axis, and the range is from 0 to 2 on the y-axis. And this gives us the appropriate depth and width. So let's denote the appropriate depth of 2 inches and the diameter of 6 inches. Since we have oriented the parabola opening up with a vertex at the origin, then we know the general equation has the form x squared equals 4ay. The bulb will be placed at the focus, which we know is a distance of a from the vertex and therefore lies at the point 0, a on the y-axis. So to determine the distance a, we will substitute the coordinates of one of the 2 points into our equation. Now let's choose the point 3, 2. We could choose the other point, and I'm just choosing this one. So substituting in x equals 3 and y equals 2 into the general equation of x squared equals 4ay, we could write 3 squared equals 4 times a times 2. And solving for a, we get that 9/8 is equal to a. So using a calculator, we can determine that the distance the focus must lie from the vertex is 1.125 inches. So in summary, the bulb must be placed 9/8 inches or 1.125 inches from the vertex. Now, even though we were not asked to do so, let's go ahead and plot the focus on our graph at the point 0, 1.125 on the y-axis.